Good morning, everybody. Thanks for being here. It's a beautiful day. I'm sure everybody would like to be outside doing something fun. But thank you for joining me. I am David Domanski. I'm an instructor with RSTI, Radiological Service Training Institute. We're based out of Cleveland, the Cleveland area in Ohio. So it's nice to be here. It's a little bit warmer here than it is at home right now. Yes, I've been with RSTI for 18 years now. Started out there way back when we still had film processors and all that stuff going on. So the technology has changed quite a bit since then, and I'm here to talk a little bit about well, where it began and where we're at now, and also to kind of take a quick pulse on why you're here. All right, who's here because they're how many biomeds do we have in the house? Lots. All right, fantastic. How many biomeds do we have in the house that are here because they want to learn more about imaging and are thinking about moving toward in that direction? All right, fantastic. We see a lot of that. We see a lot of that. It is a very natural progression to move from the biomed side to the imaging side. They are a bit different. There's not so much different as far as the technology that's concerned, but there are differences in terms of, well, sometimes the pressures that are involved. When an infusion pump goes down, it goes down your bench. When you get to it, you send up one of the 350 other pumps that went down. When the cath lab goes down, they want it back up yesterday. So if you're, or the day before, yes, preferably the day before. If you take care of the equipment properly and with a little bit of training, you know how to service proactively and check on things when there are things that are working pretty well and keep them in tune, then you have less times where it goes down, right? So that's part of our goal as field service engineers and imaging specialists, is to not only be able to fix the stuff, but to be able to recognize when things aren't quite right. Right. So like I said, I've been with RSTI for 18 years, started out in the wet processing world, and they kind of saw the writing on the wall that film wasn't going to be king forever. So they decided to get us all together. We had about 15 engineers at that time. They said, who wants to learn X-ray? I raised my hand and they sent me to RSTI. All right, and after training there, doing phase training and vendor-specific training there and other places, I covered 4 states, Wisconsin, Illinois, Indiana, and Michigan, as the entire imaging department for this small company. Learned a lot, learned a heck of a lot, but after a period of time, it was time for a change. And once you have this knowledge under your belt, the world is kind of your oyster. I mean, there's not that many of us on the planet, right? And in the United States alone, there's about 18,000 maybe diagnostic imaging service engineers at any given point. So somebody's always looking for one of us to fill a position. So I had lots of opportunities, but one of those was to come to work for RSTI. And so started out there doing I was a lab instructor. I helped out with some of the bigger classes, took care of all the equipment in the labs. We have extensive labs, lots and lots of equipment, basically everything imaging we do. And shortly thereafter, took over phase 1, introduction to diagnostic imaging service, which is this is kind of like a brief taste of that, because we've only got a couple hours, right? We're going to continue this on into part 2 of this, but I'm going to try to cover what I can. So any questions before I get started? All right, fantastic. So where did it all start? Anybody know this guy? Wilhelm Conrad Röntgen. He discovered X-rays in 1895, on November 8th of 1895. So we're coming up on the birthday of the discovery of X-rays. And some people would say that he discovered them accidentally. In reality, he discovered them accidentally while setting up an experiment that would have discovered X-rays, right? But what he was actually looking at, he was studying the movement of electrons. and he wanted to learn more about why they moved from one place to another and how they moved and what caused them to move. And so he was working with these Crookes tubes, these vacuum tubes, and he noticed that when he passed voltage and current through this tube, that some phosphorescent material that he had nearby glowed. It actually gave off visible light. And he went, this big long beard, longer than mine, right? And it's funny because that's the way a lot of scientific discoveries happen. It's not eureka, I've done it. It's like, well, that's freaking weird. What's going on over here, right? Let's dig into this. And so, not knowing what they were, he called them X-rays. He surmised correctly that the glowing of the phosphor must be caused by some invisible ray. Called them X-rays. In this case, the X stood for unknown, right? Just like in algebra, you're always solving for X. Ooh, sorry, I brought up math. But yeah, so didn't know what they were, and the name stuck. We still call them X-rays, even though we now know what they are, all right? Almost immediately, after the discovery of X-rays, they started being used diagnostically. This did win him the Nobel Prize in physics in 1901. But right up here in this corner, wish I could zoom in on that for you. This is the very first radiograph ever. Anybody know what it's of? A hand, specifically Rankin's wife's hand, right? And I bring that up because right here is not a tumor, right? It's her wedding ring. That actually carried a lot of significance in this image. Because think about this, right? It's 1895. I mean, don't even have airplanes yet, right? Don't have cars. And now we suddenly have this technology that allows us to see inside the body, right? Because up until this very moment, the only time you ever saw someone's skeletal structure was after the flesh had been removed. So the ring was there. It's like, hey, living person, not a cadaver. This isn't a photograph. It's a radiograph. And with a radiograph, that's really, you can think of it like taking a photograph. It is a static image, but really it's more like casting a shadow. But we're casting a shadow with a different type of light, right? So where are they? Where's this light fall on our spectrum? Well, X-rays are way up here. Now, if we look at the entire electromagnetic spectrum, it contains everything from radio waves through microwaves, infrared light, visible light, ultraviolet light, X-rays, and gamma rays. With X-rays and gamma rays, one of the key things to remember there is X-rays and gamma rays. Once an X-ray photon or a gamma ray photon is produced, they are indistinguishable. You can't tell them apart. The only difference between the two is the method of their production. Gamma rays are produced by radioactive decay, right? And they're used to make the Hulk and stuff like that. Right? So when radioactive isotopes decay, they give off gamma rays, alpha particles, beta particles, all that good stuff. And they're very, very highly energetic. X-rays can also be very, very highly energetic. They are among the shortest of rays, having very, very high frequency, very, very short wavelength. To give you an idea of the scale here, radio waves, here they're using a soccer field as the example, but if you were to look at the scale of radio waves, as far as their length is concerned, you could compare it, if you stood them on end, to anything from houses to skyscrapers. They're massive. Radio waves are huge. Microwaves, now we're down to about the size of grains of sugar, grains of salt, thereabouts. Infrared light around blood cells, visible light. Visible light there, the scale of the wavelength and frequency of visible light is somewhere around the scale of bacteria. So we're getting pretty small now. We get into ultraviolet light, now we're getting down to the molecular scale. X-rays and gamma rays, well, they have their own specific properties, but With X-rays, now we're down to the atomic scale. So imagine this, if we had an X-ray photon, and that X-ray photon was a soccer ball, and we were standing in Canada, and we were going to throw that soccer ball to Mexico. Maybe the Hulk's helping us out, who knows? All right. If we were throwing that soccer ball from Canada to Mexico, and the United States was part of an atom in our bodies, right? New York could be the nucleus of that atom. Los Angeles, on the scale that we're discussing here, would be the first orbital electron, the first K-shell electron, so the closest thing to the nucleus. So we're talking really, really tiny stuff here, right? That soccer ball would be the X-ray photon. So if we're throwing that to the south, going between New York and LA, the chances of it encountering anything are slim, right? So this brings us to an interesting thought. To X-ray photons, you, me, most of the things in this room, we are all made primarily of open space, right? I don't feel like open space, but maybe up here sometimes. But yeah, we're made primarily of open space. So a lot of X-rays, well, they do one of three things. They either penetrate, absorb, or scatter. And penetration is the unimpeded passage of X-rays through matter. So they're going through us like we're not even there, which means they don't do any damage. So here's your first mind bender of the day. If you're going to be exposed to radiation, do you want to be exposed to high energy radiation or low energy radiation? High. The higher the better, right? The higher the energy, the more penetrating that beam is, and the more likely it is to pass through you like you're not even there. The soft radiation, they refer to it in terms of soft and hard radiation. This basically just means within that part of the spectrum, these are longer wavelengths, these are shorter wavelengths. And that changes the energy of those. The harder the X-ray beam is, the more penetrating it is. So has anybody played around with any X-ray equipment at all? All right. What are the three things you have to select on the console in order to make an exposure? Yep, kV, MA, and time, right? kV, the high voltage that we apply to the X-ray tube. MA, the amount of current we're going to get through the tube. Time, how long we're going to have that. kV determines how hard that X-ray beam is and how much stuff it will go through. So kV selection is typically based on patient thickness, right? There's actually a formula for that. If you want to know, I can tell you. It's patient thickness in centimeters times 2 plus 30, right? So if they were X-raying somebody's pelvis, let's say their pelvis was 25 centimeters thick, times 2 would be 50, plus 30 would be 80. So 80 kV would probably be a really good starting point for that. Not that it would be perfect, because there's lots of other factors involved. What receptor technology are they using? How much filtration the X-ray system has, all that good stuff. But, all right. So we're talking about stuff on a very, 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 very fine, very, very minute scale with different properties. Like we said, X-rays can penetrate, absorb, or scatter. Visible light, well, visible light, it reflects or refracts. So that's why we can see that a shirt is gray or red or blue or whatever the case is. It's because it is absorbing all of the other wavelengths except for those wavelengths, right? But I can't tell if somebody has their back to me, I can't tell if the front of their shirt is red. Right? So I can only see the color on the back because that's what the light is reflecting off of. That's what's hitting our eyes. We see reflected light. Ultraviolet light gains some capabilities. UV light has a little bit of penetrating ability, right? Not a whole lot. Now down here in Florida, you should all be well aware of the ability of infrared light, right? I'm sorry, ultraviolet light, UVA and UVB. If you spend too much time out on the beach, what do you get? Sunburn. What's that? Crispy? Yes, sometimes crispy. Anybody ever have a sunburn bad enough that you peeled? I have. You want to know what's happening there on the genetic level? What's that? Well, yes and no. Yes, you killed it, but also a huge portion of it self-destructed. Right? So, yeah, when you get a sunburn, it is quite literally a radiation burn, right? And yes, you know, some of your skin cells were killed outright. Some of your epidermis was killed outright. But in other cases, there are points where ionizing radiation, like ultraviolet light, like X-rays, like gamma rays, um, causes mutations, and they're never the cool ones, right? So you don't get X-ray vision or stuff with superpowers. Um, but we've been evolving on this planet for quite some time. So our body has developed ways to deal with that stuff. So when we get a sunburn bad enough that we have a bunch of damaged skin cells, they may not be dead yet. This is why sometimes, you know, you get that sunburn, and if you notice, you start to look red, but things haven't peeled off yet, right? That's because the process is still ongoing. What happens is those skin cells, rather than reproduce incorrectly, self-destruct. They fall on their own swords because they know there's another layer to come up behind them. So rather than reproduce incorrectly and cause melanomas and carcinomas and all that good stuff, they just throw themselves off the cliff, as it were, metaphorically speaking. All right? But X-rays, well, yeah, they have that ability to penetrate. That's why when we get a sunburn on our skin, and we don't get like a kidney burn, right? Or a liver burn. I'm sure you'll get that when you go to some of the, you know, get-togethers later in the show, right? But it all works out, right? So we're dealing with stuff at the very, very top of that spectrum there. And in order to do that, we have to have some equipment to help us produce this stuff. Now, one thing about X-rays is we have not really changed the way we make them, right? The X-ray tube has had some changes, but that was like early in the 1930s. Let's see, William D. Coolidge came up with the hot cathode X-ray tube, and then we got rotating anode X-ray tubes. But as far as the basic function of the X-ray tube is concerned, it's been the same for over 100 years, right? X-rays, well, we said gamma rays were produced by radioactive decay. X-rays are produced by the deceleration of high-speed electrons. So basically, we create a source of electrons, we give them a whole lot of kinetic energy, we throw them at a target really hard. When they hit that target, they make a whole bunch of heat and a little bit of X-rays, right? This is not a very efficient system. Here we have a basic rad room. Okay, in this little basic rad room, well, we have our elevating table with a table bucky. We have a wall stand with a wall bucky. The bucky assembly is where our image receptor would go. This one was probably initially designed to be used with analog image receptors. It's that same style of tray, but it can be used with film, with computed radiography, with digital radiography. We have DR panels now that are the same specs, the same geometry as your film cassettes, so they can go right in there as well. But above this table, we've got a couple of items here. We have our X-ray tube, and we have a collimator. The X-ray tube is attached to a sealing tube mount, or CTM. One of the things you'll find is that manufacturers call them lots of different things. And we're kind of our own worst enemy. This is it's just a Shimadzu. It's like a DX, the MX200, something like that. I can't remember there, but it's got a number for the overhead. Some call it a CTM, sealing tube mount. Some call it the tube crane or the counterpoise. Siemens calls it the 3D because it moves in 3 dimensions and allows us to position that tube. But inside that tube, we've got some stuff going on. We have our X-ray tube insert. Now, when it comes to replacing an X-ray tube, we don't replace just the insert. We replace the whole assembly, right? Because it's there's a lot of stuff going on there. There's oil, there's all kinds of things. But this is where we're going to make that X-ray beam. And when we make a beam, we're producing not just one wavelength, we're producing a bunch of them. We're producing what I would describe as a polyenergetic beam, a beam consisting of many wavelengths and frequencies, right? Because if we go back for a second, in order to generate this image, we needed a combination of things, right? If all we did was penetrate, well, we would have blasted through everything and we wouldn't have seen anything at all. If all we did was absorb, then it would be the same as me casting a shadow of my hand up here on the screen. But we didn't do that. We have a combination of penetration and absorption. We have enough penetration to get through the soft tissue, but not so much that we're blasting through the bone. All right? So yes, we are, again, casting a shadow, but we're casting a shadow with light from that special part of the spectrum that lets us do that. Now, in this process, the patient does receive some dose. That's what absorption is. Absorbed energy is the dose. However, this is another important part. One of the big things we talk about in phase 1 is radiation safety. Any exposure to radiation causes some damage, some mutations. Now, generally, these are happening at cellular level, and your immune system takes care of the bulk of it. But there's a small portion of the damage that's done by radiation that is cumulative. It can't be repaired. If it gets right down to it, your body will repair X-ray damage at the rate of about 2.5% per day, essentially 50% repaired at the end of 30 days, and 90% repaired at the end of 90 days. But there's 10% that it just can't fix. That's what is referred to as residual dose, all right? So, but it's just that. It's like, think of it like scar tissue, right? It's not, that's one of the things I try to get through to people is like, being exposed to radiation does not make you radioactive, right? Sure, you've probably heard somebody say at some point, yeah, I was in an accident, they x-rayed my leg so many times, I probably glow in the dark. You know, it's like, it's not how it works, right? The only way you become radioactive is to be contaminated by radioactive isotopes, right? So don't do that. The deal is, with diagnostic imaging, we don't have to worry about it, as long as we're smart. Time, distance, and shielding, right? Those are the 3 main parameters that are used for radiation safety. And the number one thing is, if we're working with general rad, we should never receive any exposure at all, ever, from a service standpoint, because X-rays only exist when we want them to, right? We control when they happen, right? So, back to our basic rad room. The tube and collimator. The collimator itself, that's another one that people tend to mislabel in their brains. A lot of people think of the collimator as a beam focusing device. That is not the case. We cannot, through normal means, focus X-rays, right? Yeah, there's some stuff on spy satellites that you didn't hear about from me, but that can do that. But in diagnostic imaging, we don't do that, right? The beam is where the beam is. It's polyenergetic beam, many wavelengths and frequencies. All we can do is restrict it, right? So the collimator is not a beam focusing device. We're not taking all of this energy and squeezing it down into a smaller area. It's a beam limitation device, so that if this is the size of my image receptor and I've got my patient on top of that, there's no reason for me to expose the entire patient, right? So once I have everything lined up, if I have something like a PBL collimator, like this one here, that's a PBL stands for positive beam limitation, which is a fancy way to say an automatic collimator, right? So if I were to take my image receptor, pull out this cassette tray, put it in there, lock it into place, when I push that in, it's actually measuring the size of this. And it will tell the system what size that receptor is, and this will automatically size right down to that area. So I'm only exposing that area. Yes? No, because we're not talking about visible light, all right? I see where you're coming from. Yeah, so it's not like an f-stop or anything like that. It's literally, think of it like we're looking out a big picture window, right, at a pastoral scene, and somebody closes the drapes, right? The entire scene didn't get squished into that area, and we're not changing the focus on what's left. We're just preventing ourselves from seeing that portion. So it's kind of like that, if that helps. All right. So then, yes, we'd go over to the console, we select our KV, our MA, and our time, or that's what we would call a 3-point technique, or we would select a 2-point technique, which would be KV and mass. Some systems present it in one way, some present it in another. Big part of getting to figure out your machines is what one of our founders used to call the quirks of the system. The quirks of the system. Got to learn the quirks of the system. Each one's a little bit different. They each have different bells and whistles and different buttons and symbols and nomenclature and all that stuff. So once you know what it is for that system, we can select our technique factors, make sure that we're at the right source to image distance, that the patient is positioned properly, all that good stuff, and then they can take their shot. All right. Now, had that been on film, everything would have to be just right the first time. All right. So there are other things that they can use, automatic exposure control, stuff like that, that basically takes away the selection of timing from the user in total, right? It basically, AEC, automatic exposure control, is a timer based on radiation. So it's looking at how much dose is getting through to the image receptor. When it sees enough, it says stop, right? Because one of the simplest parts about diagnostic imaging in total is that it doesn't matter what image receptor you're using. Every single image receptor out there, whether it's film, CR, DR, we get into fluoroscopy, you're talking about, you can have flat panel detectors, you can have image intensifiers and cameras. They're all dose accumulators. They all require a certain amount of radiation to give us the image that we want to see. Right? Make sense? So any system, really doesn't matter how simple or complex it is, you can break it down into 3 basic areas: the production of X-rays, the formation of the image, and the image receptor and image processing. All systems are going to have this. Some are going to be, well, if you look at our previous slide here, this one just has a couple of cabinets in the corner. Some might have a single cabinet, some might have 6. It just depends on how many bells and whistles that particular machine has, right? Our controls can look completely different from machine to machine. This one has a keyboard and a mouse. Others will have touch screens. Some will have mechanical push buttons. They still make systems with mechanical dials, ka-chunk, 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 like rotary tap switches, stuff like that. They're still out there. One of my other duties at RSTI is I'm also the curator of our X-ray museum. And we have some stuff going back to, well, I have some X-ray tubes that are over 100 years old, but I have equipment that goes all the way back to about 1935. And some of the generators, the consoles and things that are there for some of these very, very early systems, the only difference between those and a modern single phase system is that the new one has digital displays instead of analog displays. That's really it. All right, so The technology, like I said, hasn't changed a whole bunch. What's changed is high voltage. Not how much we need, but how we develop it. So we've gone through a lot of different forms of generators, and here's a keeper. When they talk about the X-ray generator, what do you think of? If I told you to check the generator, what would you expect me to have you look at? What's that? Well, that's what it is, but yeah, you typically, when somebody says check the generator, well, the generator itself is actually the high voltage transformer, right? Now, in some cases, these were massive 1,500-pound beasts. I've got one in the museum. All right. Now, they're about the size of a bread box, right? Because they have to be due to increases in frequency and all that good stuff. But hopefully we'll have a chance to get there. But the high voltage transformer itself is the generator. But when somebody says check the generator, well, with these new transformers, you're not going to open those up. If you have a problem with one, take your phone and say, send me a new generator. All right. It isn't the way we used to do it, but that's how we do it now. So now when somebody says check the generator, they're usually asking you to check all of the supporting electronics that provide you with your primary voltage selection and your filament current selection and your timing and all that good stuff. Make sure your rotor controller is working and so on and so forth. All right. So the term generator universally abused across the industry, pretty much. All right. X-ray tubes. X-ray tubes themselves come in all sorts of shapes and sizes, from standard single-purpose rad room tubes to heavy-duty tubes that can be used for rad or fluoro, to what we call monoblock tubes that actually have the transformer built into the X-ray tube. You see those usually on low-power systems, like some of your mini C-arms and stuff like that. But yeah, there's a pantheon of tubes available out there. And things have gotten a lot simpler from the service standpoint as well, as far as tubes go. Is one of the things that we have to set up is tube protection. And it used to be a whole deal. Now we say it has this tube, save. Right? And we're pretty much done. So we've gotten simpler in that respect as well. Now, as far as the collimator and filtration goes, well, let's see what we got here. Before we get too far, our X-ray tube can be as simple as this. All right, now I wish I had one with me to show you, but this is the literal X-ray tube. This would be a glass envelope made of borosilicate glass. Think of your Pyrex baking dishes. All right, same kind of thing there. So borosilicate glass, sometimes with a controlled window thickness so that we don't get too much filtration of the beam. On the left-hand side, we have the cathode. On the right-hand side, we have the anode or target. The cathode usually contains a pair of filaments, a small filament and a large filament, that provide us with a small and large focal spot. Those do a couple of things for us. Generally speaking, resolution is controlled by focal spot size. The smaller the focal spot, the sharper the image. Right? However, the smaller the focal spot, the shorter my exposures can be. So if I need to do a longish exposure on a larger mammal, then I might need to switch to the large focal spot in order to get that kind of output. All right. On the right-hand side, this is what we would see inside a rotating anode X-ray tube. We have an anode here, the target here. You can see they've got it looking like it's made up of multiple materials, because it often is. The face of the anode will most likely be tungsten. Tungsten, atomic symbol W, which is confusing as hell until you realize that tungsten used to be called wolfram, which was a really cool name. Why'd they change it? Would you rather be wolfram or tungsten? I don't know. But, but Tungsten, atomic number 74, very, very high atomic number, which makes it an excellent target material for the production of X-rays. And it also has the highest melting point of any of the naturally occurring elemental metals, over 3,342, 3,422, something like that, degrees Canadian, which is like 6,098 degrees Fahrenheit, something like that. So, which seems like, oh my God, over 6,000 degrees, there's no way we could ever possibly melt that. We can melt it in one exposure. Because we have generators out there that are capable of up to 100 kilowatts of output. And especially if something happens and our anode isn't rotating, oh yeah, we'll melt it right quick, right? The backside of that is usually an alloy of molybdenum and some other metals, sometimes rhenium. The shaft is also molybdenum because it's really particularly crappy at transferring heat. We don't want heat to go this way because this is where our rotor is. The rotor has bearings in it. The bearings are actually part of the circuit. We conduct through these bearings, right? These bearings are inside the glass envelope. We've got a glass envelope that's connected to metal on both ends. It's a vacuum tube. Those bearings are getting lubricated once when they build the tube. Some of these tubes might last 20 years. So it's, yeah, it's probably a good idea to try to protect those bearings if we can't get in there and re-grease them, as it were. All right. So that leads us with a nice little target assembly here that's going to be rotating at one of two speeds, either 3,450 RPM for low speed or 10,000 RPM for high speed. High speed is more expensive because I have to add other stuff. I have to have a braking circuit. I have to have all the additional gear to take the stator frequency from 60 hertz up to 180 hertz. But it allows me to do much longer exposures. So if I could do maybe a 0.3 second exposure at a certain kVnMA in low speed, I might be able to do, instead of 0.3 seconds, I might be able to do 3 full seconds in high speed. So it does make a big, big difference. The whole idea behind the rotation is we have this electron beam that's going to be coming across here. And we want to present that beam with a relatively cool surface, right? It's kind of like if this laser were one of those like super high power lasers that could, melt rubber and stuff like that. And we went out in the parking lot and pointed it at the sidewall of a car tire. In pretty short order, you'd be able to see the air inside the tire, right? But if the tire's rotating, we're still hitting that same spot, but it's constantly being presented with a relatively cool surface. It would take a lot longer for us to get that thing hot enough to make it melt. All right? So, anode, shaft, rotor assembly there, cathode assembly here with our filaments. The filaments themselves are also typically made of ductile tungsten. We can thank William D. Coolidge for that, and every other incandescent light bulb that you've probably ever used. He was the inventor of the ductile tungsten filament and the hot cathode X-ray tube. Before these, we had what were called partially evacuated tubes, and they were really, really difficult to control. It was almost like, okay, I'm going to date myself. Anybody ever been to Spencer's Gifts? Right, you know the the plasma globes, where you put your fingers on there and bzzz, the early tubes kind of look like that. They were partially evacuated tubes that not only produce X-rays, but you saw, because they're just kind of hanging out in the air, you got to see the ionization of the gases inside the tube. It was kind of funky. But new ones, well, everything's inside the housing. So if we want to see the filaments glow, we actually have to remove the collimator, look in the port of the tube, all that good stuff. All right. This is all going to be supplied by our generator. Generator contains both our high voltage transformer down here and our filament transformer up here. Now, what we're looking at here, this is the absolute most basic setup we could possibly produce as far as the generator is concerned. Not as far as the tube is concerned. The stationary anode would be even simpler. But what's going to happen is our incoming power here, single phase, is going to get stepped down to about, oh gosh, somewhere between 4 to 5.5 amps of current, around 6 to 12 volts for our selected filament. And our high voltage here, well, the high voltage that's going to be supplied to the tube is going to be somewhere between 40,000 and 150,000 volts, right? The higher I go in kV, the faster those electrons are moving across that tube, or a more accurate way to put it is the more kinetic energy they have, all right? It's that kinetic energy that's going to get converted into heat and X-ray photons. About what percentage of that do you think is going to be X-rays? Yeah, maybe 1, right? So when I said we didn't have a very efficient system, that's what I was talking about. Over 99% of the energy that we put into this X-ray tube gets converted into nothing but heat. So you could kind of equate it to, if you had a piece of sheet metal, let's pretend this is sheet metal, and I was hitting the back of this with a blowtorch, and you saw the metal start to discolor, and the whole time that's happening, the entire sheet is getting hot. It's getting hotter and hotter and hotter, but eventually, right where the blowtorch is hitting, it starts to glow red. You can think of that red glow as being equivalent to the X-ray output compared to the amount of heat that's going into that, sheet metal. The metal itself is going to get pretty darn hot. All right. So in this case, we don't see any rectification or anything like that. But if I were to have my single phase AC coming in here, stepped down here, stepped up there, when it gets to the tube, the thing that we have to remember here is that the cathode is always negative, the anode is always positive, and electron flow is always from negative to positive, right? So we can only conduct from cathode to anode. We can't conduct the other way around. So if I were stepping up that voltage, anytime I was on the positive going side of that waveform, I would be conducting across the tube. But as soon as I hit 0 volts, I'd get nothing, because I can't conduct back in the other direction. That's what we would call a self-rectifying system, or a half-wave system. Never going to see one in the field. This is just to show you that even with the very simplest of setups, you could still make X-rays. All right. In reality, we're going to rectify that, so we'll have full wave rectified output, but even that's not good enough for what we want. We want to get as close as possible to pure DC across that tube to reduce the amount of ripple that we see. All right. So that source, where those electrons are striking, this is what's known as the focal spot. And the focal spot is kind of not a misnomer per se, because it is where the electrons are focused. But a lot of people seem to think that it's focusing the X-rays. It's not, right? And a big part of the problem is the way this is always drawn. Because here they're comparing the focal spot, or the perception of the focal spot, from the perspective of the cathode and from the perspective of our image receptor. Because of this angle, what's known as the target angle, when we look at the focal spot in this direction, it appears much smaller than it actually is. And therefore it acts smaller. So that's actually going to give us a sharper image. So we're able to spread out that energy over a larger area in this direction, but still have it act like a smaller area in this direction. Now, the tricky bit here is that we have a diverging beam that we always see it kind of drawn that way coming out of the X-ray tube. And it's not because this is like, we're not doing a bank shot off of the face of the anode, all right? Why do we call X-ray radiation X-ray radiation? Because it radiates. Yeah, it radiates. It radiates in all directions, right? So we have X-rays being produced at an infinite number of points within this focal spot, and they are going in every direction. The reason that you usually see this drawn as a cone coming out of the X-ray tube is because that's what we let out. All right. The X-ray tube housing itself is lined with lead. There's a port, a window in that we let X-rays out of. X-rays are still going every place else in there. We just don't let them out. All right. Ooh. Now this, we could spend half a day talking about this slide, but we're not gonna, because we don't have that much time. Oh, holy crap, we're running out of time now. All right. Phase one. A lot of the slides that we're looking at here are directly out of our phase one curriculum. And when I break down phase one on day one, I say there's three really important things in phase one, introduction to diagnostic imaging, where we are laying the bedrock, we're laying the foundation that every other class is built upon. And if you can understand these three things, then you're golden, right? One of those things is this, quantity and quality. The second thing, which we spend an entire day on in class, is the factors that affect radiographic quality, right? So a big part of what we do is learning to talk the talk. If I'm helping out a radiologist or a surgeon or a rad tech, I need to speak to them in terms that they understand, right? Pardon my French, but they don't give a shit if I changed a circuit board or bent a bracket or tightened a screw. They want to know that their image quality is better now than before I got there, right? Because another thing that happens is as you gain more and more experience, your calls become less and less, hey, my machine's broke, fix it, because you've gotten really good at, you know, preventative maintenance, you've gotten really good at being proactive, so your stuff rarely breaks. Now the calls you get are, my image sucks, fix it. Okay, what does that mean? And what does that mean to them? A lot of it's subjective. So we need to have that vocabulary. So that's the second part. The third part is understanding a basic high frequency block diagram, right, for an X-ray system, because it contains everything that we need in order to make X-rays, right? But quantity and quality, this is the stepping off point, right? Quantity is pretty straightforward. How much radiation are we making? Quality, also not difficult, right? The difficult part is separating it in your brain. Because when we're talking about quality here, when we're talking about quality and quantity here, we're talking about the X-ray beam, not the image. Beam quality and image quality are not the same. I can have an extremely high quality X-ray beam and a craptacular image. All right. So when we talk about quality, another way to think of beam quality is beam hardness or the penetrating ability. You know, we want it to be penetrating enough that it gives us what we want to see, but not so penetrating that we start losing information. All of this is controlled by our little friends, the electrons. These are the electrons that are going to be generated right here at the cathode. When we heat up that cathode, heat up that filament in the cathode, that 4 to 5.5 amp range, that takes us into the realm of what's known as thermionic emission. Man, so many new big words today. Thermionic emission, which means we get that filament so hot that we start boiling electrons off. And we create something called a space charge, which sounds super fancy, but it's just a cloud of electrons in a vacuum tube. All right. Say space charge because it's a vacuum, so we're in the vacuum of space, right? But it's a cloud of electrons. How much energy we give those electrons, when we apply kV, that controls the kinetic energy. It's like throwing a baseball. The harder you throw the baseball, the more kinetic energy you're giving it, and the more it can do when it reaches its destination. An electron with higher kinetic energy is going to produce X-ray photons of higher energy, right? So if we notice, kinetic energy is the only one here that affects both quantity and quality, right? This is not, just so you know, this is not an increase-decrease thing. It's just saying that this affects both of these. So kinetic energy relates directly to kV. kV goes up, quantity goes up, and quality goes up. They both increase. If I increase the number of electrons I have available, if I make that filament hotter, I'm going to generate a bigger space charge. I'm going to have more electrons available. If I have more electrons available, that's going to give me more MA. MA only affects quantity. Because if we didn't change the kV, we aren't changing the kinetic energy of those electrons going across the tube. We just have more of them, right? Make sense? Time, pretty straightforward, right? The longer I leave that kV applied to my tube, the more radiation I'm going to produce. Yes, sir.
If you increase the MA, does that give you, I guess, like a more detailed image?
No, not necessarily. Well, you got me there, all right? There's something called quantum model. And quantum model occurs, it's a whole long thing, but I'll try to make this as brief as possible. With quantum model, what we're saying is it takes a certain quantity of photons or quanta to generate an image. So a good way to think of it is like, let's say I took this remote and put it on this black tablecloth, and I had a sifter with powdered sugar in it, right? Because maybe I just made beignets, right? So it's, yeah, anybody wants to talk food, I'm your guy. So my wife refers to Facebook as David's cooking show. So, and if I just tapped that, we'd get some powdered sugar coming down here. And if I pick this up, maybe I could tell that there was something there, maybe I couldn't tell that there was something there. But as I continued to add powdered sugar, pretty soon I'd be able to say, oh yeah, there definitely was something there. And then before too long, I could tell you what the exact shape of that thing was, right? So if you think of it like rain in a parking lot, if you're up on top of the hotel looking at the parking lot and people are leaving, and it just starts to rain, and the pavement was dry, well, yeah, at first, yeah, I couldn't tell if there was a car there or not. And it's like, oh yeah, there was definitely something there. It's like, oh wait, there was a dually parked there and there was a hatchback parked there, right? So yes, the number of photons we have available due to the number of electrons we have produced will have an effect, but it's usually at the extremes, right? So we want to make sure we have enough. And this actually brings up an important point, because especially with film, as they made films and film screen combinations faster and faster and faster, they required less and less radiation, but you lost more and more information, right? Here's your if you take one thing away from our first part of this discussion, is that everything in diagnostic imaging is a trade-off between dose to the patient and image quality. And generally speaking, the higher the dose, the better the image. All right. So you can actually, do you ever get to play with like C-arms or anything like that? Right. So if you throw something on the II of an OEC, and you can take that MA all the way down to 0.2 MA at 40 kV, and the image will be really, really dark and really grainy. That dancing grainy pattern, what some people call the ants on the sugar cube effect, that's quantum model. You are literally seeing the packets of photons striking the input phosphor. as you increase the MA, and leave the KV exactly where it's at. As you increase the MA, you'll see the background start to flatten out and get brighter and brighter and brighter. And pretty soon you won't be able to see those scintillations because the statistical fluctuation of the distribution of the quanta of the photons has dropped to a point where it doesn't matter anymore. All right. So I don't know. Does that answer your question? Okay. Got a couple minutes left. Anybody else have any questions before we? Oh yeah, that's the chart. That's the chart in a nutshell. In fact, we talk about the chart two different ways. We go over all the main factors, right, in phase one, and then in phase two we revisit it and add on to it. So yeah, you always have to think about things like patient motion, equipment motion. We said we could select KV and MA and time, or we could select KV and mass. Mass is just MA times time in seconds. So another point here is that mass is mass is mass. If I have a mass of 10, it's like saying I have a coffee cup, right? I can fill up that coffee cup one drip at a time using a low MA over a long period of time, or all at once, high MA for a very, very short time. The high MA for the short time is going to be harder on the X-ray tube. But if I'm doing a chest film, right? Well, I hope there's some motion there. When you get a chest X-ray, they usually say, please hold your breath, right? I've never had them say, please hold your breath and stop your heart. Right. So in that case, they're actually going to, use, they're going to, well, in most cases, most techs don't worry about the machine anyway, it's not theirs. Right. So they're going to use the highest MA possible and the shortest amount of time in order to capture that image with the least amount of motion. It gets way more complicated when you get into things like CT. There are CT systems out there that, CT is just X-rays that go roundy, right? A detector on a gantry with a big honking X-ray tube. So as these are spinning and they're imaging slices of the patient, well, some of them do enough slices now that they can image the human heart in one rotation, which is sometimes less than half a second. However, if the patient's heart is beating, the system will actually monitor the patient's vitals and only make exposures between heartbeats, so they get the best possible image. Crazy. No. Well, I mean, yes and no. I mean, if they don't have to retake it, sure. Yeah, a big part of the reduction in dose comes from a reduction in repeats. So yeah, that helps a lot. All right, so like we said, we're going to make a whole bunch of heat. The interactions at the tube side will get as deep into this as you want in the second half of the program. But if you're like, yeah, good enough, we can move on. Believe me, there's a lot of stuff in there. So way more than we can talk about in 2 hours. But we'll do what we can. So any other questions before I cut you loose here?